In a universe dominated by ancient massive structures, there are places where something unexpected happens that defies the cosmic norm. New galaxies emerge. These rare formations are changing our idea of how the cosmos should behave. While the Milky Way and Andromeda seem to have entered their mature phase, somewhere out there in the far corners of space, young galaxies are still being born, glowing with a new star formation. But why do these exceptions exist? What forces allow them to thrive when the rest of the universe has slowed down? By exploring these distant regions, we learn about the forces that lead to the formation of such grand structures, the role of dark matter in all of this, and the mysterious processes that allow some galaxies to defy the passage of time. The discovery and classification of galaxies was a milestone in our understanding of the universe. In the early 20th century, observations by Edwin Hubble showed that the nebulae observed in telescopes were not just gas clouds inside our galaxy, but entire galaxies, each containing billions of stars. This discovery expanded our understanding of the cosmos beyond the Milky Way, revealing a universe teeming with distant galaxies. Soon galaxies were categorized by their shape: spiral, elliptical, and irregular. These classifications helped astronomers create a more organized view of the cosmos, which led to further study of the origin and evolution of these huge structures. However, as our observations deepened, a surprising pattern emerged. The vast majority of galaxies observed were ancient, dating back almost to the very beginning of the universe. This discovery was unexpected. When the first detailed studies of galaxies were conducted, scientists expected to find a range of galaxy ages, including recently formed galaxies. However, instead of a universe full of young galaxies still in the formation stage, they found that most galaxies had already reached maturity. These findings challenged existing theories of cosmic evolution at the time, raising questions about how and when galaxies formed. At first, the scientific community was stunned. The rarity of young galaxies seemed to contradict the ongoing process of star formation that's still observed in the universe today. This paradox, the presence of ongoing star formation in predominantly ancient galaxies, posed a serious question to our understanding of galaxy formation and evolution. As astronomers delved deeper into this mystery, they began to realize that the formation of galaxies may not be as simple as previously thought. The processes that govern the early universe, such as the distribution of dark matter and the influence of cosmic structures, seem to have played a more important role in shaping its landscape than first thought. These factors likely contributed to the rapid formation of galaxies shortly after the Big Bang, leading to a shortage of newly formed ones in the modern era. Determining the age of galaxies is a complex task that relies on a variety of methods, most of which focus on the age of the stars within them. For example, astronomers have used several methods to estimate the age of the stellar population of the Milky Way and Andromeda. One of the main methods involves studying the distribution of stars in the Hertzsprung-Russell diagram, or HR diagram, which shows the dependence of the luminosity of stars on their temperature. In particular, astronomers focus on the turning point of the main sequence, the stage at which stars begin to leave the main sequence and turn into red giants. This point is very sensitive to age. The position of the pivot point on the HR diagram can give an accurate estimate of the age of the stellar population. Another important method is the study of globular clusters, dense groups of ancient stars orbiting around the outskirts of galaxies. The age of these clusters is also determined by the rotation points of the main sequence of their stars. And since globular clusters are among the oldest objects in the galaxy, they provide crucial clues about their formation history. For example, the oldest globular clusters in the Milky Way are about 13 billion years old, indicating that the Milky Way itself formed shortly after the Big Bang. In addition to studying star clusters, astronomers also use spectral analysis. By analyzing light spectra, particularly absorption lines, they can determine the relative proportions of different types of stars. Older galaxies are dominated by red, cooler stars, while younger galaxies have more blue, hotter stars. The discovery that many galaxies, including the Milky Way, formed nearly 13.8 billion years ago, shortly after the Big Bang, was a significant breakthrough in cosmology. The rapid collapse of clouds of primordial gas under the influence of dark matter probably played a crucial role in these early formations. This process laid the foundation for the cosmic structures we see today. So the formation of galaxies in the early universe is a story deeply intertwined with the mysterious and influential presence of dark matter. In the chaotic period after the Big Bang, the universe was a hot, dense soup of particles in which matter and radiation were tightly bound together. As the universe expanded and cooled, gravity began to pull matter together into the first structures, tiny clumps of matter, known as proto-galaxies. According to scientists, dark matter played a key role in this process. Unlike ordinary matter, which interacts through the electromagnetic forces and radiation, dark matter interacts mainly through gravity. Because of this, dark matter began to stick together earlier than ordinary matter, forming the basis on which the first galaxies eventually formed. These dense regions of dark matter, often called dark matter halos, provided the gravitational wells needed to pull in gas and dust, leading to the formation of the first stars and eventually the first galaxies. These early galaxies were relatively small and simple compared to the huge and complex galaxies we see today. They were often irregularly shaped and lacking a distinct structure, such as that of the Milky Way. But over time, driven by the gravitational pull of dark matter, these proto-galaxies began to merge and interact. As proto-galaxies merged, they grew in size and complexity, forming more massive structures that eventually evolved into the spirals, ellipticals, and irregular shapes that populate the modern universe. This period of intense formation and merger is often referred to as cosmic noon, a time of active star formation and growth through mergers at a much higher rate than we observe in the modern universe. So why are newly formed galaxies such a rarity in the modern universe? One of the key factors contributing to this phenomenon was the very process of galaxy mergers. In the early universe, when galaxies were smaller and more numerous, there were frequent interactions and collisions between them. However, as the universe expanded and matured, such collisions became less frequent, resulting in fewer new galaxies. Another factor is the changing influence of dark matter halos. In the early universe, halos were smaller and more concentrated, favoring the collapse of gas and the formation of new stars and galaxies. As the universe expanded, it became larger and more diffuse, making it harder for the gas to cool and condense into new formations. The large-scale structure of the universe, often referred to as the cosmic web, also plays a notable role in this process. Galaxies are not randomly distributed, but are arranged along huge threads of dark matter that stretch across the cosmos, connecting galaxy clusters. Along these threads, gas flows into them, fueling the star formation process. However, in the present epoch, most of the gas has already been consumed or trapped in larger and more stable structures, which also leads to a decrease in the rate of new formation. However, despite all that we've just said, there are rare cases that violate this trend. One such example is the dwarf irregular galaxy known as ISWICKY 18. located about 45 million light-years away. This galaxy is notable for having a relatively recent burst of star formation. Unlike most, IceWiki 18 began its first major burst of star formation only about 500 million years ago, well after the period when most galaxies in the universe were fully formed. The slow evolution of IceWiki 18 represents an intriguing case in the study of galaxy formation. Its star-forming regions are characterized by intense ultraviolet emission and stellar winds from young massive stars. The presence of these young stars, combined with the overall low metallicity, suggests that IceWiki 18 did not undergo the same evolutionary processes as most other galaxies. This late bloom may provide clues to the conditions favoring delayed star formation and raise the question of the role of environmental factors, such as nearby galaxy interactions in triggering or suppressing star formation. Another notable case is a galaxy with a rather unwieldy name of HSC J1631 plus 4426, discovered through observations with a Subaru telescope, located 400 million light-years away. This specimen is not only young, but also holds the record for the lowest observed oxygen content. The low oxygen content indicates that the galaxy is in the very early stages of its formation and has only recently begun to convert primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The galaxy's small size, about 0.8 million solar masses, comparable to a star cluster in our Milky Way, further emphasizes its youth. The fact that such a young and small specimen exists so late in the history of the universe is surprising, given that in the early universe, the conditions for galaxy formation were much more favorable. And given that the expansion of the universe continues to accelerate, making conditions for the formation of new galaxies more and more impossible, such findings become quite extraordinary. At the same time, star formation is a continuous process that continues even in ancient galaxies. And star clusters such as the Pleiades provide clear evidence of this ongoing activity. The Pleiades, often referred to as the Seven Sisters, is a young open star cluster located just 448 light-years from Earth. Despite the age of the Milky Way galaxy being over 13 billion years old, the Pleiades cluster is a relative newcomer, having formed only about 100 million years ago. This indicates that even in such a mature galaxy as ours, there are still regions of active star formation. The formation of star clusters like the Pleiades usually occurs in regions of galaxies where there's a high concentration of gas and dust. These molecular clouds collapse under their gravity, giving birth to new stars. In the case of the Pleiades, the stars of the cluster are still relatively young and hot, and they emit bright blue light, making the cluster visible to the naked eye. Such star clusters are not unique to our galaxy. In neighboring galaxies such as the Large Magellanic Cloud, abbreviated LMC, star formation is also ongoing. The LMC, a companion galaxy to the Milky Way, contains the oldest known stars as well as regions where new ones are still forming. One such ancient star, LMC 119, that was only discovered this year, is believed by scientists to be about 13 billion years old. This discovery highlights the remarkable longevity of some stars and suggests the conditions for star formation are still not fully understood by us. These star-forming regions are not just remnants of the past, but a critical factor in the future evolution of galaxies. As new stars form, they contribute to ongoing dynamical processes in their host galaxies, affecting everything from the formation of planetary systems to the distribution of elements necessary for life. While star formation continues in some regions of galaxies, like the Milky Way, a significant factor affecting the overall evolution of these galaxies is the presence of the previously mentioned dark matter halos. These halos extend far beyond the visible edges of galaxies and play a crucial role in their formation and structure. As we know, dark matter has a significant gravitational influence on galaxies. This influence is most evident in the way galaxies rotate. Observations have shown that the outer regions of spiral galaxies, including the Milky Way, rotate much faster than would be expected with only visible matter. This discrepancy suggests the presence of a massive invisible component forming a spherical halo around the galaxy. The dark matter halo not only stabilizes galaxies, but also affects their ability to form new stars, and, consequently, new galaxies. In the early universe, dark matter halos provided the gravitational wells necessary for the collapse of gas and the formation of the first galaxies. Over time, however, these halos grew in size and became more diffuse, preventing the formation of new galaxies. The expanding halos, with their enormous gravitational influence, can prevent the gas from cooling and condensing into new stars, effectively suppressing the birth of new galaxies in the current epoch. These dynamics create a delicate balance in the cosmos, where dark matter both promotes and inhibits the growth of cosmic structures. According to scientists, the presence of such halos is one of the key reasons why we see fewer new galaxies forming today compared to the early universe, marking a significant shift in cosmic evolution. Understanding the formation and evolution of galaxies remains one of the most serious challenges of cosmology. Despite significant progress, debates about the fundamental processes that shape the universe are still ongoing. One of the key debates concerns the formation of structures in the cosmos, whether it occurs according to the top-down or bottom-up approach. According to the top-down model, large cosmic structures form first, and then they break up into smaller galaxies and clusters. According to this model, the largest galaxies and galaxy clusters appeared at the very beginning of the universe's history, and smaller structures were formed as these large structures decayed. In contrast, the bottom-up model suggests that small structures formed first, and tiny proto-galaxies and star clusters eventually merged to form larger galaxies and clusters. This theory is consistent with the observed hierarchical nature of the universe, where small objects merge into more complex and massive systems over billions of years. Although these models provide a foundation for understanding galaxy formation, recent observations have revealed complexities that challenge both theories. For example, the discovery of ancient massive galaxies in the early universe suggests a more subtle interaction between these processes, perhaps indicating that the true nature of cosmic evolution is a combination of both scenarios. Nevertheless, the search for and understanding of new galaxies continues to drive astronomical research. JWST has already opened new windows into the distant universe, allowing astronomers to peer into an era when galaxies were just forming. One of the most intriguing questions is whether new galaxies are still forming today. While the early universe was fertile ground for galaxies to form, today's cosmic landscape presents a different picture. As the universe expands and dark energy accelerates this expansion, conditions suitable for galaxy formation become increasingly rare. Future astronomical missions are poised to push the boundaries of our knowledge even further. Instruments such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission will shortly carry out deep space surveys that are likely to reveal new galaxies that have eluded previous observations. These missions are aimed not only at discovering new galaxies, but also at unlocking the mysteries of dark matter, dark energy, and the overarching structure of the universe. History of the universe is far from complete. As we continue to explore the cosmos, discoveries change our understanding and raise new questions. Each glimpse into the distant past brings us closer to unraveling the mysteries of the universe's formation and fate. Stay tuned for more discoveries to come. Are we alone? It's question is, in some ways, as old as the starlight that travels through the eons to reach us. Since the earliest civilizations, our ancestors have looked up at the night sky in wonder, their imaginations fired by the flickering lights overhead. Today, armed with the power of modern science and technology, we still await the answer to this age-old question. But our goal is not just to find primitive life, but to discover the whispers of civilizations that might share this grand cosmic stage with us. The Breakthrough Listen Project, the most ambitious search for these whispers, Technosignatures, is pushing the limits of our hearing in an attempt to capture the murmurs of extraterrestrial life. As we stand at this crossroads of discovery, several teams of scientists in the Breakthrough Listen study and other SETI projects have already published several scientific papers moving us closer to answering this question. So, how close are we to the goal in this grand quest? What non-trivial decisions have been made to ensure a seamless search for signals and improve our chances? Let's get to the bottom of it. In our celestial odyssey to unlock the mysteries of life beyond Earth, scientists have charted two major paths across the cosmic seas: the search for biosignatures and the search for technosignatures. Each path offers a unique lens through which to view the potential for life in the universe, guided by the principles of astrobiology and the advanced technologies at our disposal. Biosignatures, the chemical fingerprints of life, serve as beacons in our search for biological activity on distant worlds. These signatures are not just markers, but signs of complex interactions between living organisms and the environment. Every molecule, from the oxygen and ozone created by photosynthetic life forms to the methane and carbon dioxide produced by biological and geological processes, carries a story of potential life. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to the infrared spectrum, is our most advanced scout in this endeavor. Using transmission spectroscopy, JWST can analyze, dissect light from distant stars as it passes through the atmospheres of orbiting exoplanets. This light bears the fingerprints of various molecules, each absorbing certain wavelengths and leaving behind a spectral signature that JWST can detect and analyze. Peering into the depths of space, JWST searches out these spectral lines with precision, allowing us to infer the presence of water vapor, carbon dioxide, methane, and other potential biosignatures in the atmospheres of exoplanets. This method not only hints at the possibility of life, but also provides insight into the atmospheric composition, climate, and habitability of these distant worlds. Parallel to the search for biosignatures is the search for technosignatures, the hallmarks of advanced technological civilizations. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap to complexity, where life has evolved to use and manipulate its environment in profound ways. From radio signals to megastructures orbiting distant stars, technosignatures embody the potential to detect not only life, but also societies that may have mastered the art of cosmic communication. The pursuit of technosignatures spans the galaxy. Initiatives like the Breakthrough Listen Project utilize vast networks of radio telescopes to listen to and eavesdrop through space. These telescopes scan the sky for narrowband radio signals, anomalies in the natural cosmic radiophone that may indicate deliberate transmissions from intelligent beings. Biosignatures are whispers of life embedded in the fabric of a planet's atmosphere, providing a glimpse into invisible worlds orbiting distant stars. Among the vast number of potential biosignatures, 4 stand out for their significance: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and mysterious unexpected combinations of molecules. Oxygen, the breath of life on our planet, and its companion, ozone, form the first pair of key biosignatures. On Earth, oxygen is a byproduct of photosynthesis, the process that formed our atmosphere and allowed life to thrive. The presence of ozone, a molecule formed from oxygen by the sun's ultraviolet radiation, provides a protective layer shielding the surface from harmful radiation. The discovery of these molecules in the atmosphere of an exoplanet could indicate the presence of a thriving biosphere, perhaps similar to our own. Phosphine and ammonia, less common but no less intriguing, represent a second pair of biosignatures. Phosphine, a gas associated with anaerobic ecosystems on Earth, has been proposed as a potential marker of biological activity on other planets. Ammonia, another molecule with biological ties, may indicate the presence of life, especially in environments where it's not expected to exist in significant quantities due to non-biological processes. Methane and carbon dioxide form the third cornerstone of our quartet of biosignatures. Methane, a potent greenhouse gas, can be produced both biologically by organisms such as methanogens and abiotically by geologic processes. Carbon dioxide, a critical component of Earth's carbon cycle, is a product of respiration and volcanic activity. The simultaneous presence of methane and carbon dioxide, especially in unexpected ratios, may hint at biological processes in nature. Finally, with the fourth point, we move into the realm of unexpected combinations of molecules, methane and carbon dioxide, which cannot be stably present in more or less large quantities simultaneously without being transformed into other substances. Such combinations defy conventional expectations and point to the possibility of life functioning based on alien biochemical processes. The James Webb Space Telescope, JWST, humanity's most advanced observatory, is designed to study the atmospheres of exoplanets in search of these very biosignatures. Using transmission spectroscopy, JWST studies light from a star as it passes through a planet's atmosphere during its transit. When light passes through atmospheric gases, certain wavelengths are absorbed by the molecules, leaving behind a spectral fingerprint that JWST can detect and analyze. On the other hand, technosignatures, like the fingerprints of advanced civilizations, offer a different path in our quest to discover not just life, but societies that have reached a level of technological sophistication, perhaps similar to or even superior to our own. Unlike biosignatures, which hint at the mere presence of life, technosignatures speak of the ability of civilizations to alter the environment on a grand scale, communicate across the stars, and harness energy in ways we're only beginning to imagine. Technosignatures cover a wide range of signals and structures, from radio waves unintentionally emitted by a planet's communication networks to deliberate beacons aimed at the stars, from colossal energy collectors known as Dyson spheres to the barely perceptible glow of city lights on the exoplanet's night side. These signatures, if detected, will not only indicate the presence of life, but will also provide deep insights into the technological capabilities of alien civilizations. Our own planet is a prime example of a world teeming with technosignatures. Every radio broadcast, every satellite, and every piece of space debris orbiting the Earth creates a symphony of signals that, to the distant observer, unmistakably indicate the presence of an advanced civilization. The very fabric of our daily lives, from global communications networks to space probes venturing into the unknown, generates a cascade of signals that radiate out into space, making our presence known to all who can hear us. But why are technosignatures a more accurate way to search for technologically advanced civilizations? The answer lies in their specificity and the intentional or significant nature of the signals and structures they represent. While biosignatures can occur from simple microbial life to complex ecosystems, technosignatures clearly indicate a level of technological development and intent. The discovery of a technosignature not only confirms the existence of life, but also indicates that this life has crossed the threshold of cognitive, technological capability, engaging in activities that leave an indelible mark on the cosmic canvas. Breakthrough Listen was launched in 2016 with an ambitious mission to scour the cosmos for signs of technologically advanced civilizations. The project represents one of the most comprehensive searches for alien technosignatures ever undertaken. Armed with state-of-the-art technology and unprecedented scope, the project utilizes some of the most powerful radio telescopes in the world, including the Green Bank Telescope and Parkes Observatory. These colossal ears, tuned to the quiet whispers of the universe, can detect a range of signals, from faint radio emissions from distant stars to potential transmissions of extraterrestrial origin. At the heart of the mission is the desire to detect technosignatures, signals that, by their nature, can only be produced by technological means. These can range from narrowband radio signals that differ from the natural background noise of space, to powerful laser pulses that cut through cosmic clutter. The project had previously focused on the Milky Way galaxy for strategic reasons, to begin the search in our cosmic neighborhood, where such signals may be strongest and most detectable. The Milky Way, with its billions of stars, provides fertile ground for such work. Each observable star is a potential sun for other planets. Each planet a potential cradle for life as we know it, or life yet to be imagined. The project was originally designed not just to search for signals in our galaxy, but to explore in depth the nature of life and intelligence in the universe. Sifting through the cosmic expanse of the Milky Way looking for signs of life is akin to searching for a single word spoken in a whisper in the middle of a bustling metropolis. A galaxy of about 100 billion stars can easily conceal the signals of other civilizations. The task of monitoring such a vast array of targets for technosignatures is monumental, not only because of the large number of stars, but also because of the complex array of cosmic phenomena that can obscure or mimic the signals we are looking for. The problem is compounded by the limitations of our current technology and the limited resources at our disposal. Even with the most advanced radio telescopes, we can only listen to a small fraction of the stars in the galaxy at any given time. Huge distances dilute the signals, making them fainter as light years pass, and various natural cosmic phenomena such as the emission from pulsars and nebulae add further complexity to the search. In the face of these challenges, astronomers and scientists have looked beyond the familiar boundaries of the Milky Way to the wider universe. By observing galaxies as individual entities, each made up of billions of stars, we can try to pick up the cumulative signals of advanced civilizations. This extragalactic strategy is based on the premise that a sufficiently advanced civilization can harness technologies that affect its entire galaxy, from building megastructures like Dyson spheres to harnessing the energy of supermassive black holes. Such grandiose endeavors could lead to technosignatures that, in theory, could be found in vast intergalactic voids. The transition to extragalactic studies comes with some challenges, from even greater distances to the need for more sensitive instruments and more sophisticated methods of data analysis. Nevertheless, each galaxy observed and each dataset analyzed brings us closer to understanding whether we're truly alone in the universe or part of a grander galactic world. Extragalactic exploration is exactly what Carmen Choza and her team did in 2023. Using the Robert C. Byrd Green Bank Telescope, the team has embarked on an ambitious mission to observe the centers of 97 nearby galaxies, studying them for 5 years. This work, one of the largest of its kind, used to search for narrowband Doppler drift, in 4 frequency bands from 1 to 11 gigahertz. The goal was to detect signals that could come from civilizations capable of using energy equivalent to that of a Kardashev Type II civilization. The most important aspect of this study was the implementation of the TurboSETI pipeline, a sophisticated tool designed to search for Doppler drift. This pipeline played a crucial role in analyzing the vast amount of data collected during the study. To combat the persistent problem of radio frequency interference, called RFI, which often mimics extraterrestrial signals, the team adopted an on-source, off-source cadence pattern. This method involves alternating between observations of a target galaxy, on-source, and a nearby region devoid of the target, off-source, and is repeated 3 times for each galaxy. Because RF interference and localized noise are present regardless of the telescope's pointing, they'll appear in both on-source and off-source observations. In contrast, a true astronomical signal should only manifest itself in observations from the source and not in the observations beyond the source. This approach helped to distinguish real astronomical signals from terrestrial interference, which improved the reliability of the results. Despite careful methodology and advanced technology, the study faced significant challenges, primarily due to radio frequency interference. The team's innovative radio interference mitigation strategies, including signal injection and recovery tests, were crucial in differentiating terrestrial and potential extraterrestrial signals. These efforts emphasize the difficulty of finding technosignatures, especially since signals must be significantly more powerful than those detectable within our galaxy to be considered extragalactic. The exhaustive search resulted in 6,034,313 hits across all observed galaxies. These matches represent cases where the data analysis pipeline has identified signals that potentially stand out from the background noise and may be of interest for further study. From the original 6,034,313 matches, further refinement and analysis using a computer algorithm narrowed the field to 1,519 events of particular interest. These events were then scrutinized by the research team, which attempted to distinguish potential extraterrestrial signals from the all-pervasive RFI noise. Despite the complexity, the team eventually concluded that all 1,519 events were associated with terrestrial sources, or natural cosmic phenomena. However, the work done by Chosa and her team not only illuminates the path we've traveled, but also beckons us to new horizons. The ability to reanalyze data through the subtle prism of machine learning promises us a chance to uncover signals that previously remained obscure or were perceived as noise. This changing landscape of SETI research, constantly enriched by technological innovation, invites us to look deeper. As we move forward, armed with improved tools and a deeper understanding of the challenges that await us, the search for extraterrestrial technosignatures continues. In the meantime, we'll be eagerly awaiting new opportunities to solve the mysteries of the cosmos. What if the closest star to our Sun is hiding a world where humans might one day live? In 2016, astronomers discovered Proxima Centauri b, a planet just 4 light-years away. But getting to this distant neighbor isn't just a dream. It's a challenge that modern science is beginning to address. Imagine a journey of more than 25 trillion miles. The technology we have today, such as the ion engines used in deep space missions, pales in comparison to what would be needed for such a journey. But hidden in the blueprints of a decade ago and cutting-edge research are the keys to interstellar travel. But distance isn't the only obstacle we have to overcome. Today, we'll talk about it and find out if humanity's next giant leap can take us to Alpha Centauri. The dream of interstellar travel has been part of the human imagination for centuries. wasn't until the 20th century that science began to catch up with science fiction. The journey begins with a momentous moment in 1961, when Yuri Gagarin became the first man to orbit the Earth. This achievement paved the way for space exploration, proving that humans could survive and work beyond our planet. Then came the Apollo program, including the historic 1969 lunar landing. Neil Armstrong and Buzz Aldrin's footsteps on the lunar surface were not only victory for humanity, but also a demonstration of our ability to reach and explore other celestial bodies. In the 1970s, Voyager missions provided invaluable data on the outer planets and heliosphere. These probes, now in interstellar space, carry with them golden records, messages intended for any intelligent extraterrestrial life that might encounter them. The voyages of Voyager 1 and Voyager 2 have given us a glimpse of the vastness of space and the inspiring potential of travel beyond our solar system. But humanity does not stand still. In recent years, the development of advanced propulsion systems has been crucial. Ion engines, used in missions such as NASA's Dawn spacecraft, enable long-duration missions with unprecedented efficiency. These engines use electrically charged particles to generate thrust, a method far more efficient than traditional chemical rockets. At the same time, our understanding of the universe has been revolutionized with the discovery of exoplanets, planets orbiting stars outside our solar system. The first confirmed exoplanet discovery occurred in 1992, when astronomers discovered 2 rocky planets orbiting a pulsar. This discovery shattered previous notions and opened the floodgates to the search for other worlds. In 1995, the discovery of 51 Pegasi b, the first exoplanet found orbiting a sun-like star, further reinforced the idea that planets are fairly common in the universe. This gas giant, located about 50 light-years away, ushered in an era of exoplanet discoveries that continues to this day. Among the most exciting discoveries is Proxima Centauri b, discovered only in 2016. This exoplanet orbits Proxima Centauri, the closest star to our Sun, at a distance of only 4.24 light-years. Proxima Centauri b is in the habitable zone of its star, where all the conditions for liquid water to exist could exist. This proximity and potential habitability make this planet a prime target for future exploration and even potential colonization. The discovery of Proxima Centauri b was made possible thanks to the radial velocity method, which allows you to detect subtle fluctuations in the motion of the star caused by the gravitational pull of the orbiting planet. So far, this method has helped to identify more than 1,000 exoplanets, each of which has become the next step in the search for a world on which life may exist. The feasibility of interstellar travel depends directly on our ability to develop efficient and powerful propulsion systems. Current space travel technology has made significant advances, but it still falls short of what's needed to travel beyond our solar system. Ion engines represent one of the most advanced forms of space propulsion in use today. Unlike traditional chemical rockets, which use explosive reactions to create thrust, ion engines use electricity to ionize the propellant, usually xenon gas. The ionized gas is then accelerated using an electric field, creating sustained and highly efficient thrust. NASA's Dawn spacecraft, launched in 2007, is a prime example of the capabilities of ion propulsion. Dawn's mission was to explore the asteroid belt, in particular the protoplanet Vesta and the dwarf planet Ceres. Ion propulsion allowed Dawn to enter and exit orbits around these bodies, which would have been prohibitively expensive with conventional rockets. Ion engines have a high specific impulse, which means they use fuel much more efficiently than chemical rockets. This efficiency is critical for long-duration missions because it allows spacecraft to take less fuel with them. However, the trade-off is that ion engines produce much less thrust than chemical rockets. This makes them unsuitable for launching spacecraft from the Earth's surface, where enormous thrust is needed to overcome gravity. Another milestone in the development of modern propulsion technologies was NASA's New Horizons probe. Launched in 2006, the spacecraft was supposed to explore Pluto and its moons, providing mankind with the first images of this distant world from an incredibly close distance. The probe's journey did not stop at Pluto, but continued on to the Kyper Belt, a region filled with icy bodies and remnants of the formation of the solar system. New Horizons used a combination of chemical propulsion and gravity assists to achieve its high speed. After launch, the spacecraft received gravitational assistance from Jupiter, which increased its speed and directed it toward Pluto. This maneuver allowed New Horizons to travel more than 3 billion miles in just 9 years. An amazing accomplishment considering such vast distances. While New Horizons demonstrates the height of current space travel capabilities, it also highlights its limitations. Despite speeds of more than 36,000 miles per hour, it took the spacecraft nearly a decade to reach Pluto, and even longer to continue its journey into the Kyper Belt. For interstellar travel, where distances are measured in light years, we need propulsion systems capable of much higher speeds over long periods of time. Meanwhile, the most intriguing and historically significant advanced propulsion concepts is nuclear pulse propulsion. This technology, conceived during the Cold War era, involves using a series of controlled nuclear explosions to propel a spacecraft. The concept was first proposed by physicist Stanislaw Ulam in the 1950s and later developed into the Orion project. The basic principle of nuclear pulse propulsion is relatively simple. Small nuclear bombs are thrown behind the spacecraft and detonated, and the resulting explosions provide powerful thrust. A large pusher plate attached to the spacecraft absorbs the force of the explosion, propelling the spacecraft forward. The potential of the Orion project was enormous. Calculations showed that such a spacecraft could reach speeds of up to 10% of the speed of light, making it one of the fastest of the proposed propulsion methods. Such a capability would significantly reduce travel time to nearby star systems, including our neighbor, Alpha Centauri. Meanwhile, in recent years, the Breakthrough Starshot initiative has become one of the most ambitious attempts to achieve interstellar travel within our lifetime. The goal of this international science project is to send a probe to the same Alpha Centauri and possibly reach it in just 20 years. Breakthrough Starshot's main innovation is the use of a light sail propelled by an array of powerful ground-based lasers. This light sail, which is a thin and highly reflective sheet, will accelerate to extremely high speeds by transmitting momentum from millions of laser beams. Unlike traditional propulsion methods, this system carries no fuel, making it extremely lightweight and, in theory, capable of speeds up to 20% of the speed of light. Realizing this technology, however, is not without its challenges. The proposed laser array would require a total optical power of about 100 gigawatts, about 100 times the capacity of the world's largest battery. Synchronizing the roughly 100 million lasers to focus their beams on the light sail is a daunting technical hurdle. To solve this problem, researchers from the Australian National University have proposed using a laser guide satellite to help maintain an accurate target throughout the voyage. Despite such challenges, the potential benefits of this technology are enormous. If successful, the Breakthrough Starshot mission will be able to transmit detailed scientific data and images from Alpha Centauri, providing unprecedented insight into our nearest neighboring star system. While light sails represent a promising near-future technology, other cutting-edge concepts are pushing the boundaries of our understanding of physics. A Among them is the theoretical warp drive. Inspired by Einstein's general theory of relativity, a warp engine would manipulate space-time itself, compressing space in front of the spacecraft and expanding it behind, allowing the craft to travel faster than the speed of light without violating the laws of physics. The concept of warp drive gained attention after the 1994 publication of a paper by physicist Miguel Alcubierre, who proposed a theoretical basis for such a drive. Although the concept is currently speculative and requires exotic matter with negative energy density, warp drive remains a tantalizing possibility for future interstellar travel. Another innovative concept is the Freeman-Dyson interstellar jet engine. This hypothetical propulsion system would harness the energy of a star, using a series of mirrors or lenses to focus stellar energy onto a spacecraft. The collected energy would then be converted into thrust, propelling the spacecraft at high speeds. While Dyson's concept is intriguing, its practical realization faces serious obstacles. Capturing and converting enough stellar energy to achieve meaningful thrust would require materials and engineering capabilities many times greater than our current technology. Perhaps the most powerful of the proposed propulsion systems is a propulsion system based on antimatter. Antimatter, coming into contact with matter, annihilates both particles, releasing huge amounts of energy. A spaceship powered by antimatter can theoretically reach speeds approaching a significant fraction of the speed of light. The potential of antimatter propulsion is staggering, but so are the challenges. Antimatter production is currently a highly inefficient and expensive process, and its safe storage represents additional challenges due to its highly reactive nature. Despite these obstacles, antimatter research continues as it promises to be an unprecedentedly efficient engine. Huge distances present the most obvious obstacle. Nevertheless, even with a modestly efficient propulsion system, only a fraction of the difficulties would be overcome. Interstellar travel is an enormous undertaking fraught with technical and logistical challenges. Even with the most advanced propulsion systems, traveling to our nearest star system, Alpha Centauri, requires overcoming enormous technical obstacles. One of the main technical problems is protection against radiation. Space is filled with high-energy particles from the Sun and distant space sources. Prolonged exposure to this radiation can be deadly to both humans and sensitive electronic equipment. Modern spacecraft use a combination of physical and electronic shielding to protect against radiation, but these methods are insufficient for the prolonged exposure expected during interstellar travel. Advanced materials and innovative shielding techniques are being explored. These include the use of magnetic fields to deflect charged particles and the development of new composite materials that provide better protection without excessive weight gain. However, creating effective and lightweight radiation shielding remains a major challenge. Another technical hurdle is maintaining the structural integrity of the spacecraft themselves over the long term. Spacecraft designed for interstellar travel must be able to withstand the stresses associated with launch, long stays in space, and possibly collisions with micrometeoroids and other space debris. The high speeds required for interstellar travel exacerbate these risks, since at such speeds even tiny particles can cause significant damage. Engineers are exploring advanced materials such as carbon composites and reinforced alloys to improve spacecraft durability. In addition, modular designs that allow for in-flight repair and maintenance could be critical for long-duration missions. The vast expanse of space presents another logistical challenge. Even at a significant fraction of the speed of light, it would take decades to reach the nearest star systems. Advances in autonomous systems and long-term life support are needed to keep a spacecraft operating reliably for such a long time. Solutions such as hibernation or suspended animation are already being explored, but these technologies are still in the experimental stage. In addition to technical and logistical challenges, interstellar travel faces serious economic and political obstacles. The cost of developing, building, and launching an interstellar mission is astronomical. No pun intended. Governments, private enterprises, and international consortia will have to collaborate and pool resources. Historically, space exploration has been funded primarily by national governments, but the growing involvement of private companies such as SpaceX and Blue Origin suggests a potential shift to more diverse funding models. The search for habitable planets, especially in the Alpha Centauri system, is one of the key areas of modern astronomy. As you may have already realized, the discovery of Proxima Centauri b in 2016 was an important milestone that showed the possibility of habitable worlds in our nearest neighboring star system. This exoplanet has sparked numerous missions and research initiatives aimed at figuring out its characteristics and potential to support life. To continue this research, the European Southern Observatory has developed a new instrument designed specifically to search for exoplanets in the Alpha Centauri system. This advanced instrument, part of the Very Large Telescope in Chile, enhances our ability to detect Earth-like planets by improving the accuracy of radial velocity measurements. The instrument aims to identify Earth-sized planets by detecting the tiny gravitational fluctuations they cause in their host stars. Focusing on Alpha Centauri A and B, the two sun-like stars in the system, this instrument seeks to detect additional planets that may lie within their habitable zones. The improved sensitivity and resolution of this technology promises to reveal planets that have not previously been detected, giving a clearer picture of the potential for habitable worlds in our nearest star system. The importance of discovering a habitable planet in the Alpha Centauri system cannot be overemphasized. Such a discovery would be a tremendous step forward in our quest to understand how widespread habitable conditions are beyond our solar system. A habitable planet in such close proximity would be a prime candidate for future interstellar missions and a potential target for human colonization. Recent discoveries in the search for habitable exoplanets have been promising. For example, late this spring, astronomers discovered the Earth-like exoplanet Gliese 12b, located just 40 light-years away. This planet, comparable in size to Venus, orbits a red dwarf star and is estimated by scientists to have a surface temperature of about 107 degrees Fahrenheit. The discovery of such a planet, which may have an atmosphere, provides insight into the conditions necessary for a planet to retain an atmosphere and for liquid water to exist. The discovery was made possible by NASA's Transiting Exoplanet Survey satellite, which detects exoplanets by observing a small, dimmer star as the planet passes in front of it. During such transits, the star's light passes through the exoplanet's atmosphere, allowing astronomers to analyze its composition using transmission spectroscopy. The significance of Gliese 12b goes beyond its potential habitability. It serves as a valuable point of comparison for understanding why Earth and Venus, despite their similarities, have very different environments. By studying Gliese 12b, scientists hope to learn more about the atmospheric retention and evolutionary pathways of Earth-like planets orbiting cold stars, which are the most common type of stars in the Milky Way. Gliese 12b's estimated size may be as large as Earth or slightly smaller, comparable to Venus in our solar system. Current efforts to find and study potentially habitable planets around Alpha Centauri and other nearby stars continue to evolve. Instruments such as JWST are expected to play a crucial role in this search, providing a deeper understanding of the conditions that could make these planets habitable. On the other hand, no one is saying that humans should be the first to explore these distant worlds. Even without the advanced technology necessary for human survival, we can still send probes to pave the way. Intelligent robotic probes and artificial intelligence have a key role to play in the future exploration of interstellar space. These technologies can operate autonomously, handling complex tasks without direct human intervention, making them ideal for long-duration missions far beyond our solar system. One of the most intriguing concepts in this regard is the so-called von Neumann probes. These theoretical, self-replicating machines could explore the galaxy using local materials to create their replicas, exponentially increasing the number of probes with each replication. This approach could provide extensive exploration and potential colonization without requiring constant resupply from Earth. However, when it comes down to human space exploration, the idea of interstellar arcs and self-sustaining habitats represents a visionary approach to colonizing distant star systems. These massive spacecraft would host large communities, providing everything needed to sustain life during multi-generational journeys to other stars. These habitats will be equipped with advanced life support systems, agricultural facilities, and social infrastructure to ensure the well-being of their inhabitants. In conclusion, while our current technology limits us to relatively modest space travel, these advanced concepts offer a glimpse into a future in which we can transcend the space barriers that confine us to our solar system. As technology advances, these concepts may well move from science fiction to reality, paving humanity's path to the stars. What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of space-time to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown, guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new, uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes. This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1. The Infinite Universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2. The Post-Inflationary Multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life. Of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, they share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3. The Many Worlds Interpretation of Quantum Mechanics. Perhaps the most disconcerting of Tegmart's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the many worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the many worlds interpretation, at the moment of the coin flip, the universe is split into 2, one where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe, and the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4. Ultimate Ensemble. The fourth level of Max Tegmart's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible, but this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws, essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth to the sensations it evokes when we eat it, can be described using math. In this way, this simple fruit becomes a small, tangible proof of a much larger truth. Our entire universe, from the smallest atom to the largest galaxy, can be part of a grand mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe that a consistent set of mathematical rules can describe exists as surely as our own. It implies that universes with radically different properties that defy our physical intuition are just as real as our own. Consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter formation and evolution. Or imagine a universe governed by a different type of geometry, where the shortest path between 2 points is not a straight line, but some other curve, which radically changes the structure of the universe and the life it can support. Level 4 is connected to the other levels of the multiverse, providing the ultimate framework. While levels 1 to 3 deal with the universes that differ in initial conditions, physical constants, or quantum results, Level 4 encompasses all possible mathematical realities. It offers a cosmos where the boundaries of possibility are limited only by the limits of the mathematical imagination. The implications of the multiverse theory go beyond physics and into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that with all its complexity and beauty, our universe is just one of countless others, each with its own history, laws, and perhaps even life forms. In the scientific realm, the multiverse theory raises profound questions about the nature of scientific inquiry and evidence. Since other universes in the multiverse are, by definition, beyond our observation, the theory walks a fine line between physics and metaphysics, forcing us to reflect on views of the principles of empirical science.
That's one small step for man, one giant leap for man.
As we ponder the vastness of the universe and the possibility of countless worlds in the multiverse, our quest for space exploration continues to propel us forward. The next chapter in human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, onward toward Mars, and eventually beyond our solar system. In conjunction with international and commercial partners, NASA's Artemis program marks a major milestone in our efforts to explore the Moon. Named after Apollo's twin sister, the Artemis program aims to return humans to the Moon by the mid-2020s, with the lofty goal of a sustained human presence there by decade's end. Unlike the Apollo missions, which were short-term visits, Artemis envisions a long-term presence of humans and robots on the Moon, utilizing its resources and using it as a testing ground for technologies needed for deeper space exploration. The Artemis architecture includes Gateway, an orbital lunar outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond.
Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of the international cooperation in space. In turn, the red planet Mars has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for manned missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, and a better understanding of the psychological and physiological effects of long-duration space travel. Human missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to search for signs of past life, test the possibility of existence on Martian soil, and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar travel, expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light-sail spaceships capable of traveling to our nearest stellar neighbors, such as the Alpha Centauri system. These spacecraft could theoretically be accelerated to a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 2 decades after launch. Such missions could provide invaluable data on other star systems and potentially habitable exoplanets, paving the way for future interstellar exploration. The journey to the Moon, Mars, and ultimately to the stars is not just a series of missions, but a continuation of our fundamental quest to explore, to understand, and connect with the universe around us. Even stepping into the next chapter of human space exploration can push the boundaries of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter,
a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? In the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1. Which leads to repeated gravitational interactions at the same point of the particle's orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies.
leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1 to 2, 2 to 3, or 3 to 4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to a different orbit, leaving the resonance gap-free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kyper Belt, lies another fascinating story of celestial harmony. Neptune, the 8th planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the 9th, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3-to-2 resonance gravitational lock, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings, and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tom Bow's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Planitia, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Planitia is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world
filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kyper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kyper Belt objects, or KBOS. Like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies, each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kyper Belt landscape. The Kyper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kyper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kyper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kyper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kyper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system.
The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kyper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the 9th planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kyper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kyper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. In the 21st century, humanity finds itself at a crossroads at a moment in history when we can see the stars, but not yet touch them.
Born in the era between exploring our own planet and the possibility of reaching other worlds, we stand on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and our place in the universe. Imagine a future in which Earth faces an existential threat, a catastrophic collision with an asteroid, a climate collapse, or something completely unforeseeable. Our solution? Build generation ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generation ships traveling at a significant fraction of light speed could travel vast distances between stars. With technology such as matter-antimatter engines, compact fusion drives, and even black hole propulsion, what seems like science fiction could become a reality. But these ships are not just vessels. They are lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenge of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth, with its social structures, cultural heritage, and daily challenges. What would it take to build such a ship? How can its inhabitants survive and thrive? Join us as we delve into the intricacies of interstellar travel without exceeding the speed of light. Today, we'll try to unlock the secrets of how humanity can one day travel to the stars, but not in an instant, but through generations. Planning for interstellar travel is not only about technology, but also about predicting why such travel might become necessary. Foreseeable threats to humanity's survival may force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself: comet impacts. Throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate shifts. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already led to significant changes in our climate: rising temperatures, melting polar ice caps, and increasingly severe weather events. If these trends are not controlled, Earth could become hostile to human life, making searching for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carries significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios where humanity faces a threat from its own creations. Uncontrolled AI or engineered pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as a defense of our species. In search of a new home, Proxima Centauri b is a prime candidate. Located just 4.24 light-years away in the Alpha Centauri system, it is the closest known exoplanet that's in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient of life for humanity. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that's smaller and colder than our Sun, meaning the planet would have to be much closer to its star to be in a habitable zone. This proximity, while favorable for retaining heat, also exposes the planet to flares and radiation, which must be considered when planning human habitation. Current research indicates that the planet has a mass similar to Earth's and may have a rocky surface. However, much about it remains unknown.
including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be needed to collect more data and assess its suitability for life. Sending a spacecraft to our nearest neighboring star involves not only covering the distance, but also ensuring that the distance is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri b was chosen as our target because of its relative proximity and potential habitability. However, reaching and inhabiting the distant world will be a monumental task requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, where one crew sets off and reaches their destination within their lifetime, seem increasingly impractical when it comes to the vast distances between the stars. This is where the concept of intergenerational ships come into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sustaining ecosystems with not only one crew on board, but all of their descendants. Life on a generational ship is designed to mimic a small self-contained world with living quarters, food production, water recycling, and social systems. The concept is simple, yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that for many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure that the inhabitants survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population, to cultural and educational programs that preserve and pass on vital knowledge and skills. Einstein's special theory of relativity presents a serious problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases and they require exponentially more energy to continue accelerating. This effectively makes traveling faster than the speed of light impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory. By accepting the duration of space travel and planning for generations of life aboard such ships, humanity can aspire to distant stars. Such an approach recognizes the limitations imposed by the theory of relativity, while at the same time supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, not the least of which is the vast distance between celestial bodies. To make interstellar travel feasible within a human lifetime, we have to take a closer look at the advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time on board is slowed down compared to the time experienced by an observer at rest. This means that for a spacecraft traveling at a significant fraction of the speed of light, the travel time of the crew will be shortened compared to those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, time dilation would cause 1 year aboard the ship to be equivalent to more than 2 years on Earth. Because of this effect, interstellar journeys stretching over decades or centuries may seem shorter to the crew, although they do not shorten the actual distance.
Several advanced propulsion methods have been proposed to achieve the high speeds required for interstellar travel. Each method has its own set of problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets, potentially allowing spacecraft to reach significant fractions of the speed of light. However, producing and storing sufficient antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun, to produce energy. By combining light atomic nuclei, such as hydrogen, with heavier nuclei, these reactors could provide sustained and powerful thrust for spacecraft. While controlled fusion technology is promising, it's still under development, and building a compact and reliable reactor suitable for spaceflight is another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the enormous gravitational energy of a black hole to propel a spacecraft. The idea is to create a small artificial black hole and harness the energy of the Hawking radiation it emits. Theoretically, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes is still in the realm of something fantastic, far beyond our current capabilities. However, the problems don't end with thrusters. Traveling at near light speed is fraught with many dangers. One of the main ones is the threat posed by interstellar particles. At these high speeds, even tiny particles can cause significant damage in a collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious hazard. High-speed space travel exposes the crew to intense cosmic radiation that can have deleterious health effects. Effective radiation protection and possibly even medical intervention will be a necessity to keep the crew healthy during long-duration missions. Maintaining the structural integrity of the spacecraft over the long term is also critical. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the voyage. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. By researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we're taking crucial steps toward reaching for the stars and expanding our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it's important to explore both best practices and traditional methods. One promising approach is to scale up the traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravitational assists to achieve unprecedented speeds. The probe is traveling at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light and makes it the fastest man-made object to date. Its propulsion system is based on hydrazine thrusters, powered by solar energy, which showed the potential of using existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase the speed of a spacecraft without expending additional fuel. By carefully planning a trajectory, a spacecraft can gain significant speed, reducing travel time over vast distances. This technique, while insufficient by itself for interstellar travel, can be an important component of a multi-stage propulsion strategy. Scaling up these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are highly efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. For faster travel, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is the Orion project, first proposed in the 1950s. This method involves a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the spacecraft forward. The Orion project uses a massive pusher plate at the rear of the spacecraft, designed to absorb shock waves from explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still have to be solved. Controlling the timing and directions of explosions requires precise design, and the spacecraft in turn must be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be carefully considered, which may also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would make it possible to travel to the nearest stars within a human lifetime. Fusion propulsion offers a more controllable and potentially safer alternative to the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still under development. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, safety, and performance. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts such as the Orion and Daedalus projects promise the potential for faster and more ambitious interstellar travel. Ensuring the survival and health of the crew over multiple generations is a cornerstone of generational ship planning. One of the most important aspects is maintaining genetic diversity, which is necessary to prevent inbreeding and genetic diseases that could jeopardize the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over many generations. By introducing various parameters such as initial population size, mutation rates, and reproductive patterns, these simulations can provide insight into the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. They also take into account possible random events, such as accidents or disease, that could affect the population. Such modeling is essential to creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be educated about the importance of genetic health and the steps necessary to maintain it. This includes monitoring genetic diversity and making informed decisions about partnership and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies by scientists such as Frederick Moran and Camille Belufi, who have extensively studied the genetic dynamics of small isolated populations. In their research, Moran and Belufi use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that with a balanced sex ratio and optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding will not jeopardize the health and viability of future generations. An initial population of 100 individuals should grow to 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The modeling takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes to ensure the sustainability of the population. Designing a generational ship to accommodate a growing population involves planning for adequate living space, resources, and social structures. The ship should provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. And this includes collaborative activity spaces and private living quarters to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it's vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for mission success. Effective crew and population planning is essential to the success of a generational ship. Using advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. Above all, however, designing a generation ship capable of sustaining human life for centuries involves creating a self-sustaining environment that mimics the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources such as water and air. These systems must be reliable, efficient, and able to operate autonomously for long periods. One of the most important aspects of ship design is the creation of artificial gravity to maintain the health and wellness of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To counteract these effects, generation ships can use rotating media to create a centrifugal force that mimics Earth's gravity. The most practical design involves a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes the occupants outward, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a rate of about 3 revolutions per minute to create an artificial gravity of 1 g, similar to Earth's. This design not only helps maintain physical health, but also provides a familiar environment that can alleviate the psychological challenges of living in space. Rotating habitats can include living quarters, recreational areas, and workspaces designed to optimize the use of available space and resources. Reliable and efficient food production systems are also required to sustain populations for generations to come. Hydroponic and aeroponic systems offer solutions for growing crops without soil, using nutrient-rich water or mist to nourish the plants. These methods are highly efficient, use less water and space than traditional farming, and are well suited to the controlled environment of our ship. Hydroponic systems involve growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to the roots. Both systems can grow a wide range of crops, from leafy greens to root vegetables, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and breeding will be able to increase the yield and nutritional value of crops. Efficient water and air recycling is critical to the sustainability of a generation ship. Water recycling systems must be capable of recovering and treating wastewater, ensuring a continuous supply of clean water for drinking, cooking, and irrigation. Advanced filtration and purification technologies such as those used on the International Space Station are already achieving high levels of efficiency. On the ISS, for example, the water reclamation system can recycle up to 98% of wastewater, including urine and sweat. This level of efficiency is necessary for long-duration missions when resupply from Earth is not feasible. Ships of future generations will need to improve this efficiency even further, aiming for near-complete recycling to minimize the need for large water reserves. Air recycling is equally important, requiring systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen but also contribute to the psychological well-being of the crew by providing a connection to nature. Projects such as Biosphere 2 have demonstrated the potential for creating closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of such systems, providing valuable lessons for the design of life support systems on generational ships. Creating a self-sustaining generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the very pillars of this design, enabling humanity to embark on a long-term journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship. It requires meeting the mental, social, and educational needs of the crew, ensuring their health, motivation, and cohesion throughout the long voyage. Isolation and confined spaces can significantly affect morale and mental health. Lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, depression, and anxiety. Addressing these issues is critical to maintaining a stable and motivated crew. Virtual reality technologies offer promising solutions for mental health and cultural connection. By creating immersive simulations of terrestrial environments, virtual reality or VR can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, helping to alleviate feelings of isolation and maintain a connection to their home planet. Artificial intelligence can also play an important role in supporting crew mental health. AI therapists, such as NASA's Simon 2.0, can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflict. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to mission sustainability. A comprehensive education system must be put into place to ensure that each new generation receives the necessary skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar voyage requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technology such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will create the foundation for a thriving community across generations. When we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species. Among the thousands of lifeless planets, it's impossible to find one as picturesque and alive as the Earth, which seems to violate the very laws of the cosmos. All life that has ever appeared on this planet owes its existence to water. The first complex molecules, the first organisms, the first humans, all of them have their roots in water. But how did so much liquid water appear on Earth, among desert planets? For all of science, the place of origin of water remains a mystery. Whether water originated in the hellish bowels of the young Earth or millions of light years away in inaccessible depths of space is a confusing question for all scientists. But the closer we get to the solution, the closer we will get to answering the question, are we alone? Today, we'll try to find the sources of water and life on our planet, diving into the very beginning of the solar system and find out why water chose the Earth, saving it from the fate of Mars and Venus. Approximately 70% of the Earth's surface is covered by water. The imposing number of bodies of water on the planet seem to us to be something quite ordinary, and based on what we know about the birth of planets, the Earth should have been completely dry. Let's go back to the very beginning of the life of our solar system. We're looking at a young sun, which has just formed from the remnants of an ancient supernova, which left a giant plume around it, a protoplanetary disk of dust and gas that spread over hundreds of millions of kilometers due to nuclear processes in the star. Many of the planets we know today, including the Earth, will be formed from these building blocks in billions of years. Since the only materials that could exist around the Sun at that time were stone and iron, the four nearest planets were formed from them. According to a recent study by the California Institute of Technology, the planetesimals from which the Earth was formed consisted of dry, stony materials. These building materials did not contain volatile substances such as water. In particular, gas was unavailable in the early stages because it was mostly ejected beyond the orbit of Mars, so an atmosphere was out of the question. But wait, what does the atmosphere have to do with it? In the early days, the Earth did not have a moderate temperature as it does now. The disk was very hot, and the Sun was very active, which is why instead of water, seas of magma were pouring out on the planet under deadly UV radiation. Therefore, there was no way that water could be retained on such a hot Earth in liquid form. And because there was no atmosphere, water could not accumulate as steam. The magmatic period could have lasted for several tens of millions of years until the surface cooled down. And, according to many studies, including those of the University of Chicago, water began to appear after that. But how did that happen? The Earth couldn't have formed with an ocean because it would have boiled over due to the hot protoplanetary disk. It would have become a scorched, dry planet like Venus, for example. Instead, water spilled into its interior, which created the conditions for the emergence of all life that exists today. So how could water get to the dry Earth? Perhaps the answer to this mysterious question is right above us. Water could have been brought to Earth by extraterrestrial messengers traveling through space. No, we're not talking about alien life forms, but ordinary comets and asteroids. In a groundbreaking study conducted by scientists using NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA,
water was first detected on the surface of the asteroid Bennu. The presence of water molecules in the rocks of Bennu indicates that such asteroids could have delivered water to Earth in the early days of the solar system. The discovery was made possible thanks to SOFIA's unique capabilities, which include a powerful telescope mounted on a Boeing 747 SP aircraft. By flying over 99% of the Earth's atmospheric water vapor, SOFIA was able to capture infrared waves that are otherwise blocked, allowing for precise observations of the composition of Bennu's surface. Comets are composed of frozen gases of rocks and dust and orbit the Sun in highly deformed elliptical orbits. They're actually snow comets that carry a lot of water and other building materials, such as methane, ammonia, and carbon dioxide. As they approach the Sun, comets melt, releasing clouds of water vapor that are captured by the Earth's gravity. Asteroids are the remnants of the primordial solar system during its active formation. They also had a significant impact on filling the Earth with various important elements, such as silicate rocks, iron, nickel, etc., depending on the class of composition. For example, the most common chondritic asteroids, or Class C, have up to 13.5% water in their composition, the molecules of which could be transported as space dust. Therefore, it seems very likely that comets and asteroids may be behind the global appearance of water on Earth. The carbonaceous asteroid Bennu is considered to be a time capsule from the early solar system, containing valuable clues about its formation and evolution. The discovery of water on Bennu adds to the growing body of evidence that carbonaceous asteroids may be important sources of water and organic compounds essential for life. The presence of hydrated materials on Bennu, which form in the presence of water, suggests that Bennu's parent body had liquid water in the past. This also means that Bennu, or similar asteroids, could have been water carriers to the early Earth, contributing to the formation of the planet's initial water supply. In particular, in the period from 3.8 to 4.1 billion years ago, the inner planets of the solar system experienced a strong bombardment by asteroids and comets, better known as the Late Heavy Bombardment. This event may explain the abundance of water on the planet, but it still requires in-depth research, such as the craters on the Moon, which were probably left by the bombardment. The atmosphere also did not stand in the way of these travelers, so asteroids and comets freely entered the Earth's space, accumulating the first water. According to the research of space chemists led by Nicolas Dauphaz, about 10% of water could have been brought to Earth by comets and asteroids. Along with asteroids and comets, meteorites are another candidate. Meteorites are fragments of asteroids or comets. The most likely source of water could be molten meteorites, which have been floating around since the formation of the solar system. However, recent studies of this type of meteorite have shown that they have a very low water content. But all is not lost for meteorites. There are several other types, including carbonation chondrites and enstatite chondrites. Despite their complicated names, these two species are currently considered to be the most likely source of water on Earth, as they contain up to 20% water on average and could even bring 3 times as much water to Earth as our oceans have now. Over time, as the Earth cooled and geologic activity decreased, it took the first steps toward the developing plate tectonics. The movement of these plates formed new mountains and ocean trenches, contributing to the system of water transfer from rivers to oceans. Plate tectonics also allowed water to be stored in the Earth's evolving mantle, motivating geologic activity and thus the formation of water within the planet. Constant bombardment by cosmic bodies also continued to fill the Earth with water. Thus, water arrived on the Earth almost continuously, gradually covering its revitalized surface with water. The still young Earth, which was just beginning its active internal formation approximately between 2.5 and 4 billion years ago, did not have sufficient opportunities to drain water into, for example, the mantle, due to its limited capacity. Therefore, the combined efforts of asteroids, comets, and internal activity could have completely covered our Earth with water,
making it a complete water world without a hint of land. In 2021, scientists from Harvard University, led by Junji Dong, conducted a geochemical study of the planet's water reserves. To their surprise, it turned out that the Earth's original ocean could have been 1 to 2 times larger than it is now. According to Junji Dong, this ocean could have flooded 70 to 90% of the early continents. A group of scientists calculated and compared the approximate amount of water in the mantle today and billions of years ago, and found that the ancient mantle could not hold as much water as it does now. This means that residual water would have to be stored on the Earth's surface. This theory can change our entire understanding of how the ancient Earth developed and, in particular, all life. Currently, theories about the origin of living organisms in shallow ponds with a mixture of different minerals and building blocks on land or in hydrothermal substances at the bottom of the ocean are popular. However, the global ocean may upend these assumptions, requiring new explanations of how life came to be or a revision of what we know about the conditions for its formation. For example, scientists are already putting forward the first theories about where organisms evolved. Thomas Carroll believes that protected water pockets in oceanic rocks may be the answer to this question. Yet, if the Earth had remained a water world, the continents and life forms we know would never have formed. The delicate balance between the water brought by asteroids and comets and the Earth's tectonics has made the planet ideal for habitation. And if there was too much water or too little, Junji Dong says, nothing would work. But only extraterrestrial space bodies could not form and maintain an ocean for a long time. Venus and Mars also experienced bombardment, but they failed to retain much water on their surfaces for a long list of reasons. And one of these reasons is the location and temperature regime in the solar system. As long as Venus is too close to the Sun and Mars is too far away, the Earth seems to be in an ideal place to maintain water in liquid rather than gaseous or solid forms. Such a place in planetary systems is called the Goldilocks zone. This zone, which is most suitable for the emergence of life, differs in each system depending on the type of star. For us, it exists between 0.99 AU and 1.7 AU, right on the edge of the zone. Without the Goldilocks zone, the water that comes to us through external pathways would evaporate or turn into ice. Moreover, the ideal zone maintains the water cycle, regulating weather and climate, and balances the functioning of ecosystems. The Goldilocks zone played an equally important role in the formation of the Earth as a habitable planet, supporting and storing water and all the additional elements brought from outside and formed within the Earth itself. All of the above theories and assumptions require careful and serious research to finally establish the full story of water's origin. The recent discovery of Bennu emphasizes the importance of ongoing research to understand the origin of water on Earth. Such research not only supports existing theories, but also provides new knowledge and evidence, deepening our knowledge of the early solar system and potential sources of water. Missions such as OSIRIS-REx, which collected samples from the surface of Bennu, aim to return these samples to Earth for detailed laboratory analysis. These samples will provide unprecedented information about the mineralogical and chemical properties of Bennu, further illuminating its role in the history of the solar system. But in fact, researching this issue is by no means an easy task. First of all, the water that scientists are most interested in is hidden deep underground under the oceans. The water is likely to have a different composition than seawater, so it would be possible to find out exactly what the main sources of water were. Therefore, scientists are probably currently using the wrong DH, deuterium to hydrogen ratio, for the Earth, which is the main method of comparing the chemical composition of the Earth and other cosmic bodies. However, it's still extremely difficult to get to the mantle. Although scientists have already had some success in this direction, having drilled a mile under the floor of the Atlantic Ocean for the first time, where they retrieved the first pieces of the mantle. But full-fledged and high-quality water studies are still far from being conducted there.
Despite this, the difficulty is further complicated by the insufficient sample of comets and asteroids to study the correlation between their chemical composition and water bodies on Earth. The protoplanetary disk around the Sun, as it moves away from it, has a completely different ratio of deuterium to hydrogen in its composition. Therefore, it's difficult to determine where the space body that brought the water could have formed in order to better understand its composition and amount of water. In addition, the diversity of water sources requires a multifaceted study to determine the contribution of each group of objects. To solve this problem, it's only necessary to study several space bodies at different distances to determine which population of space bodies is responsible for water on the planet. But today scientists can only measure the closest and brightest objects. The water on Earth itself can also confuse the trail due to changes in its composition over millions of years. The search for what filled the Earth with water will take a long time, but gradual improvements in analytical methods and future research missions will one day shed light on the sources of our life, including our own. Scientists continue to work in the hope of advancing our understanding of how water got into the solar system. In 2021, cosmochemist Laurette Piani from the University of Lorraine analyzed a very rare type of meteorite called enstatite chondrite. The isotropic composition of this meteorite is similar to that of the Earth, and it's likely to be a remnant of planetary material from the outer solar system. According to the study, these meteorites could have brought 3 times as much water to Earth as our oceans have now. Moreover, the isotopes of hydrogen and nitrogen on enstatite chondrites match those found in the mantle, which also indicates that most of the atmospheric air could have come from these rocks. However, the composition of seawater does not quite match that of meteorite water. It is possible that other space bodies could have mixed with the water, changing its original chemical content and confusing scientists. On the other hand, a group of scientists led by Edward D. Young put together a completely unexpected theory that could move space objects from the first place in the group of the main sources of water on Earth. Most of the water could have appeared on the planet from former magma oceans, where oxygen interacted with hydrogen in the early atmosphere. The interaction of magma and hydrogen produces water. This amazing process does not negate the impact of asteroids, comets, and meteorites, but rather adds to the history of water on Earth. Finally, in June 2023, another stunning theory emerged that goes against what we know about the formation of the Earth. According to this theory, instead of water appearing on Earth due to cosmic bodies, our planet was attracted mostly by pebbles and ice particles from the protoplanetary disk in the early stages of its existence, like a vacuum cleaner. Thus, the presence of water doesn't depend on a random event like comet bombardment, according to lead author Isaac Agnet, and therefore the Earth could have formed in as little as 3 million years instead of hundreds of millions of years. This theory could overturn all knowledge about the formation of planetary systems and the origin of water in particular, so it needs a lot more careful research to make its mark even louder. The history of water on Earth is one of the most intriguing questions for modern science. Scientists propose many theories and assumptions based on studies of samples as old as the Sun itself, getting closer to the desired solution every day. Whether brought by comets, meteorites, and asteroids, or formed by the Earth itself, water is fascinating for its mystery and ability to shelter and sustain life. And one day, its mastery will be tamed, and we will finally know how the Earth came to life.